I remind you, let's see, the situation with the witch's cauldron was this. The first important thing is that there were, all right, whoops, so this is the big cauldron here. This is the one whose height is 1 meter and whose width is 2 meters. And it's a parabola of revolution here, and it had about approximately 1,600 liters in it. And this curve was y equals x squared. And the situation that I described at the end of last time was that the initial temperature was T is equal to 0 degrees Celsius, and the final temperature, instead of being a constant temperature, we were heating this guy up from the bottom, and it was hotter on the bottom than on the top, and the final temperature was given by the formula T is equal to 100 minus 30 times the height y. So at y equals 0, at the bottom it's 100, and at the top T is just equal to 70 degrees. Okay, so this is the final configuration for the temperature. And the question was, how much energy do we need So the first observation here, and this is the reason for giving this example, is that it's important to realize that you want to use the method of disks in this case. The reason, so it doesn't have to do with, you shouldn't think of the disks first, but what you should think of is the horizontal. We must use horizontals because T is constant on horizontals. It's not constant on verticals. If we set things up with shells, as we did last time to compute the volume of this, then T will vary along the shell. And we'll still have an averaging problem, an integral problem along the vertical portion. But if we do it this way, T is constant on this whole level here. And so there's no more calculus involved in calculating what the contribution is of any given level. So T is constant on horizontals. Actually, in disguise, this is that same trick that we have here. We can factor constants out of integrals. You could view it as an integral, but the point is that it's more elementary than that. All right. Now I have to set it up for you. And in order to do that, I need to remember what the equation is, which is y equals x squared. And the formula for the total amount of energy is going to be volume times the number of degrees. That's going to be equal to the energy that we need here. And so let's add it up. It's the integral from 0 to 1, and this is with respect to y. So the y level goes from 0 to 1. This top level is y equals 1. This bottom level is y equals 0. And the disk that we get, this is the point x comma y here, is rotated around, and its radius is x. So the thickness is dy, and the area of the disk is pi x squared. And the thing that we're averaging is t. Well, we're not yet averaging, we're just integrating it. We're just adding up the total. Now I'm just going to plug in the various values for this. And what I'm going to get is t, again, is 100 minus 30y. And this radius is measured up to this very end, so x squared is y. So this is pi y dy. And this is the integral that we'll be able to evaluate. Yeah, question. So is it... All right. Well, let's carry this out. Let's finish off the calculation here. Let's see. This is equal to, what is it equal to? Well, I'll put it over here. It's okay. It's equal to 50 pi y squared minus, right, because this is 100 pi y, and then there's a 30, right? This is 100 pi y minus 30 pi y squared, and I have to take the antiderivative of that. So I get 50 pi y squared, and I get 10 pi y cubed, evaluated at 0 and 1, and that is 40 pi. Now, I spent a tremendous amount of time last time focusing on units because I want to tell you how to get a realistic number out of this. And there's a subtle point here that I pointed out last time that had to do with changing meters to centimeters. I claim that I've treated those correctly. So what we have here is that the answer is in degrees, that is Celsius, times cubic meters. These are the correct units. And now I can translate this into Celsius is spelled with a C. There, that's interesting. Celsius. I can translate this into units that you're more familiar with. So let's try 40 pi degrees times meters cubed, and then do the conversion factors. First of all, there's 1 calorie per degree times a milliliter. That's one conversion. And then let's see. I'm going to have to translate from centimeters, so I have here 100 centimeters per meter cubed. So these are the two conversion factors that I need. And so I get 40 pi times 10 to the 6th, that's 100 cubed. And this is in calories. Right? So how much is this? Well, it's a little better, maybe, to do it in 40 pi times 1,000 kilocalories, because these are the ones that you actually see on your nutrition labels of foods. And so this number is around 125 or so. Let's see, is that about right? Let's make sure I've got these numbers right. Yeah, this is about 125, 40 times pi. And so one candy bar, this is a Halloween example. So one candy bar is about 250 kilocalories. All right? So this is a half a candy bar. So the answer to our question is that it takes 500 candy bars to heat up this thing. Yeah. Okay. So that's our example. Now, yeah. Question. Say it again. What does the integral give us? This integral is the integral represents the following thing. So the question is, what does this integral give us? So here's the integral. Here it is rewritten so that it can be calculated. And what this integral is giving us is the following thing. You have to imagine the following idea. You've got a little chunk of water in here, and you're going to raise it from 0 degrees all the way up to whatever the target temperature is. And so that little milliliter of water, if you like, has to be raised from 0 to some number, which is a function of the height. It's something between 70 and 100 degrees. And the one right above it also has to be raised to a temperature, although a slightly different temperature. And what we're doing with the integrals, we're adding up all of those degrees. And the calorie represents how much it takes, 1 calorie represents how much it takes to raise by 1 degree 1 milliliter of water, 1 cubic centimeter of water. That's the definition of a calorie. And we're adding it up. So in other words, each of these cubes is one thing, and now we have to add it up over this massive thing, which is 1,600 liters, and we have a lot of different little cubes, and that's what we did when we glommed them all together. That's what the integral is doing for us. Other questions?